In this problem, we are given a sequence of numbers and we want to determine the sum of this sequence. So first, we need to determine the pattern. So you'll notice that going from 9 to 6 causes us to subtract 3, but going from 6 to 4 causes us to subtract 2. So this tells us that this is not an arithmetic sequence because we're not adding or subtracting a constant value. So next we'll test to see if this is a geometric sequence. So are we multiplying by the same value repeatedly? And remember that number is called your common ratio. Now this might not be one that you can just see on your own quickly what you're multiplying by. So you may need to go ahead and actually compute the ratio between these consecutive terms and see if it's constant. So we'll take the second term divided by the first term. 6 divided by 9. And that simplifies to 2/3. Now we'll do that again, this time taking the third term divided by the second term. So 4 divided by 6 also simplifies to 2/3. So right now it looks as if our common ratio is 2/3. But we'll go ahead and check the next two consecutive terms, 8/3, and divide it by the previous term, which is 4. So that's 8/3 divided by 4. Remember, that's really 8/3 times the reciprocal, 1/4, which is 8/12, which when you simplify gives you indeed 2/3. So this tells us two things. We know that this is going to be a geometric sequence of numbers, and we know that the R value, the common ratio, is 2/3. Now, since we're interested in finding the sum of this sequence, we can use our sum formula for a geometric sequence of numbers. And we call this a partial sum. We're summing up a specific number of terms in this sequence. So the partial sum for a geometric sequence of numbers is found by multiplying the first term times 1 minus r, the common ratio, raised to the n power, all divided by 1 minus r. So we'll go ahead and begin to utilize this formula, knowing that my first term in this case is 9, and we just found our common ratio is 2/3. But we now need to raise the 2/3 to the n power, and we don't know the value of n. Remember, n is the number of terms in this sequence. So I'll leave that as a question mark for right now, and then we'll divide by 1 minus 2/3. So right now we're looking at needing to figure out what's the value of n. So I know my last term is 128 over 243, but I don't know which term that is. Is that the 6th term, the 10th term, the 12th term? That's what we don't know. So we kind of have to say time out right now for this formula for the sum and figure out first how many terms there are in the sequence. So we could certainly do that just by brute force, by continuing to multiply by 2/3. So you could certainly do that by hand and just continue multiplying by 2/3 times by 2/3, and eventually you would get to the number 128 over 243. But that can be a little bit cumbersome, and we're looking for a more efficient method. That would not be very efficient if there were something like 100 terms in the sequence, some large number. So instead, we'll utilize the pattern again. Since it's geometric, we know that our formula for this pattern, or this sequence of numbers, can be found by taking the first term, a sub 1, times r raised to the n minus 1 power. So right now, I know my first term is 9, my common ratio is 2/3, and again, I don't know what n is, so this will just stay n minus 1. However, I do know that the last term is 128 divided by 243. So I can go ahead and substitute that in here for the last term, and then we'll be able to actually solve for n. Now, this is an exponential equation. So we need to start by isolating the exponential quantity. In other words, we need to isolate the 2/3 raised to the n minus 1 power. So we'll go ahead and divide both sides by 9. So 128 divided by 243. When we divide by 9, that's the same as multiplying by 1/9. And then that will isolate the right-hand side, which is the exponential quantity, 2/3 raised to the n minus 1 power. So we'll end up with 128 divided by 2,187. So this is still an exponential equation, and we have two options for solving exponential equations. We can either try to get the bases to be the same, or we can rely on our knowledge of logarithms and solve this equation with logarithms. So I'm going to go ahead and try to do it without logarithms, trying to get the bases to be the same. And you can certainly use your calculator for this. Since the numerator on the right-hand side is a 2, then I'm going to look at the 128, and I'm going to, using my calculator, try to figure out what power of 2 is going to give me 128. So for example, I know that 2 to the 5th power is going to be 32, and 2 to the 6th power is going to be 64. So it looks like 2 to the 7th power is going to be 128. And then if you check the denominator, the 2187, let's see if that's a power of 3. So using your calculator, you can check and see if that will be 3 to the 7th power, since it was 2 to the 7th power to give us the numerator, and you'll see that indeed it is. 3 to the 7th power is 2187. So this means that we can take the fraction on the left-hand side, and we can rewrite this as 2/3 raised to the 7th power. And now we've achieved the goal of getting the bases to be the same. So the uniqueness property with exponential equations says once the bases are the same, then we can set the exponents equal to one another. If the bases are the same, then the exponents must be equivalent, which gives us 7 is equal to n minus 1. Adding 1 to both sides, we see that n is equal to 8. So that means that there are 8 terms in this sequence. So now, backtracking, let's go back to our sum. Now that we know that this last term here is actually the 8th term, we can now substitute in place of that question mark that I had earlier. We can go ahead and substitute in 8. So that'll be 2/3 raised to the 8th power, the 8th power. And then right now, definitely pause the video and get your calculator out, because you want to practice entering this on your calculator so that you don't make any sort of calculator keystroke mistakes. Some things to think about as you're doing that. You definitely need to have parentheses around this entire quantity, 1 minus 2/3 to the 8th. And also pay attention to the 8. The 8 is located inside those parentheses. So it's only the 2/3 that's getting raised to the 8th power. And then depending on what calculator you own, you also may need to have parentheses around the denominator. Remember, those of you that are working on a TI-84, you have a fraction shortcut key, so you can actually enter this exactly as I have it written here using that vertical fraction notation. But if you're working on a TI-83, then you'll have to utilize more parentheses. So it turns out when we enter this, we can simplify it to an exact fraction of 6,305 divided by 243. And if you want to check the decimal equivalent of that, it's approximately 25.95. So this would be the exact form of the sum, and then we have the approximate value of this sequence of numbers, the sum of this sequence of numbers. Part B asks us to write the sum using sigma notation. So we've already found the sum, now we just want to practice writing this sequence of numbers. If it's a sequence that we're adding, then it becomes a series. We want to write this series in sigma notation. So we already have our formula for this particular sequence, which was 9 times 2/3 raised to the n minus 1 power. And we want to start by substituting in n equals 1, because if we do so and substitute in a 1 here, then we'll end up with 9 for the first term, which is exactly what we want. Then we just need to figure out what's the last value that we want to substitute in so that we get 128 divided by 243 as the last term. And we found that that was 8. There were 8 terms in this sequence altogether, so then we would end at 8. And this is how the series would be written in sigma notation.